Okay, so now that you've convinced yourself that you can increase the power and lower the alpha or keep the alpha constant or what have you as a function of the sample size, you can see that the three are interrelated. But for the moment, let's keep alpha constant. Then if we look at the power curves and compare the power curves when alpha is constant with n equals 1, here it is for n equals 1, that's the one we saw before. I've superimposed when n equals 2 what the power curve, so this is the theoretical calculation when n equals 2, and you can see what happens. So now you can get an idea. For example, if the mean was 120, if you look at the plus 20 mean on the diet, you don't have a very high chance with one flab rat of classifying it properly. What should we say? This is what, about 30% or so. So that's about 0.3. Whereas if 2 flab rats had escaped, then your power zooms up and almost doubles to about 60%, almost 60. So almost at 0.6. Okay. In fact, if we had 4 flab rats, so now we've got a total prison outbreak, then here's the curve for 4. You can see that the power increases. So now even at 20, with 1 flab rat at 20, we said it was about 30. Now if we go up to 4 of them, then we're almost at 90% or so. So this is almost 90%, 87% or something like that. Okay? So what we get, in summary then, the power increases. Now, from before we had that the power increases as the separation, so as the separation of the two means increases, and or now we've got a second reason why the power is increasing, and that is if the sample size increases. Now, so here's a clean version of the last graph we had, and the reason I brought this on is to just make one more point, how these things sometimes are read. Now, for example, suppose we want to ask the question, how well will we be able to detect a difference in the means of our diets? For example, let's say we zero in on 0.8. So if I had power of 0.8, how small a difference would I be able to detect in the means? So what I do is I come out at 0.8, and there I cross the 4 line, then the 2 line, and then the 1 line. So the 4 line, I come down, and this is my attempt at a straight line, is what? That should be about, it hits the axis at about 17, let's say 117. So that would be plus 17. All right. So what this says to us is if we had 4 flab rats, then we would have an 80% chance of detecting a difference in the diet of plus 17. Anything beyond that, we'd have even more power. We'd be up here, and so we would have even more power. Whereas, if we only had 2 flab rats, so if we only had a sample of size 2, how big a difference would we detect with 80% power? And the answer is, what should we say? This is at about 128. So let's say that's plus 28. So we would have an 80% chance of detecting a diet whose mean is 128. So it's plus 28 beyond the null distribution. And if we only had one flab rat in our sample size, then let's bring it down to 140. It's not, it's a little bit more, 141. So let's just say that's plus 41. So we would be able to detect a diet whose mean is at plus 41 over the null with 80% power. So this is how we design studies. We say, all right, if we have 80% power, how big a difference do you want to detect? Determine the sample size you will need to detect that difference.